Consider the following seemingly bizarre question. Can you draw a shape with finite area and infinite perimeter? If you want to take the time to pause and think about this yourself, now would be a good time to do so. Start first with a square, whose side length is 1 unit long. Directly underneath that square, draw another square with side length 1/2. Continue again with another square directly beneath that second, with side length now 1/3. And at this point you can probably guess that the nth square will have side length 1/n. Our entire shape will be the collection of all these squares glued together as we let the number of squares continue infinitely. Just from this description, it might be tempting to guess that both the perimeter and the area are infinite. But we'll start with the perimeter. By unraveling all the squares and placing them in a line, the question becomes whether this line has a finite or infinite length. We could imagine recording the current length after the unraveling of each square, keeping track of a cumulative growing sum, and then asking what value that cumulative sum reaches. Let's dive deep into understanding the perimeter. Start by considering only the outside boundary of the squares, which is at most 3 of the 4 sides. This is a pretty rough estimate, and as we'll see, it's actually easier to factor this 3 out, since it's part of every term, and we're really interested in the middle. Now, this summation in the middle is special. It has a name. It's called the harmonic sum, and it's often written in a more compact summation notation, like this. The way that we'll break down this sum is by comparing it actually to a simpler sum, which hopefully we can understand. So, underneath each term, here in the harmonic sum, we'll consider a different fractional power of 2. So, we're going to start with one term of 1/2, and then add on 2 terms of 1/4, and add on 4 terms of 1/8, and if we kept going, we would add on 8 terms of 1/16. This is going to keep on going and going. It's not going to stop. If we compare each term on the bottom with the term directly above it, notice that the bottom term is always less than the term on the top. Also, notice that each power of 2 in the denominator, there's half as many of those terms in the summation. So for example, for the 1/8 terms, there's 4 of those. Now we can group together the similar powers of 2, and notice that actually they always sum to 1/2. So each increment will take twice as many terms, but there will always be enough powers of 2 to do so. This represents an extremely slow but inevitable growth of the sum, meaning that we will eventually pass every number and never converge to a finite value. Now, since the harmonic sum is actually greater than this sum, it too must also diverge and approach infinity. This is a proof that actually came out in the 13th century. Now for the area. Again, since the side length of the nth square is 1/m, the area would be 1/n squared. So we can again group the terms together into a summation notation. And to break down this one, we'll also compare it with a different sum. So we can again write this out. And underneath it, this time we're going to compare it to a different summation sequence of powers of 2. So here we're going to have squares of fractional powers of 2. And each term on the bottom, this time is actually at least as large as the term on the top, which actually contrasts the previous situation. So in this case, the sum on the bottom is going to be greater than the sum on the top. Now, so for each power of 2, the number of terms is equal to the power of 2 in this case. There are 4 terms of 1/4 squared, 8 terms of 1/8 squared. So grouping these terms together, this time will simply sum to the reciprocal of the power of 2. So the 2 terms of 1/1/2 squared will sum to 1/2. The 4 terms of 1/1/4 squared will sum to 1/4. The 8 terms of 1/8 squared will sum to 1/8, so on. This sum, famously, which adds the half of the previous amount with each term, sums to 2, And since this bottom sum reaches a finite value and is greater than our original sum, the original sum must be less than 2, so it must converge also to a smaller but finite value. And that's all we need to show that this sequence of squares, stacked on top of each other, has an infinite perimeter, but a finite area of less than 2. So this should be pretty mind-boggling. It certainly was for me. And although this isn't the only shape we can construct with this property, it is a visual illustration of the fact that adding up the reciprocals of the natural numbers grows slowly, but not slow enough to converge to a finite value. But just taking the squares of those values drastically changes the result.